In Chapter 13, we're going to focus on the topic of solutions. And in this section, we'll look at the first four parts of Chapter 13, dealing with what a solution is, different types of solutions, and in particular, solutions of solids dissolved in water and gases in water. And the chapter starts out with a case study about a tragedy that happened in the summer of 1986 in Lake Nyos, Cameroon in West Africa. And what happened was that a large amount of carbon dioxide that had been held or trapped at the bottom of the lake very suddenly bubbled out of the lake and flowed down into the adjacent valley. Now, if you're not familiar with carbon dioxide, it's heavier than air and it will flow like a liquid, and the other issue is that it pushes out the oxygen in its wake. So the carbon dioxide was at the bottom of the lake and it was being held in solution by the pressure of the water above it. So the gas was actually dissolved in the water. But then the layers of the lake were disturbed, and we'll talk about how they were disturbed in a minute, but it basically allowed the carbon dioxide to come very suddenly out of solution due to the decrease in pressure, much like opening the cap on a soda bottle, and it had very lethal consequences. So to understand a little bit better the situation, Lake Nyos is a water-filled volcanic crater, and then the carbon dioxide came from molten volcanic rock that was beneath the lake. It allowed the gas to seep into the lake and into the bottom of the lake through kind of the plumbing system of the volcano. And because this carbon dioxide was bubbling up from this volcano venting into the lake, the concentration of carbon dioxide that built up in the water would increase with increasing pressure. The higher the pressure, the more gas would dissolve in the water. So because there was a large amount of pressure at the bottom of this lake, because it was very deep, it allowed the concentration of carbon dioxide dissolved in the water to get very high. So that carbon dioxide, as long as nothing disturbed the system, would remain dissolved at the bottom. But over time, it can become so concentrated that some of the gaseous carbon dioxide can escape. The bubbles of gas that came up out of it disrupted the stratified layers of the lake water. So when we say stratified, basically there were layers that contained different levels of carbon dioxide. And these rising bubbles kind of started mixing everything together, and it allowed the highly concentrated carbon dioxide and water mixture at the bottom to start coming up. It started basically churning up the lake. And as that mixture came to the top, the pressure was released, as I said, like opening the top on a soda bottle. And you know what happens when you open a soda bottle that's under pressure? Well, that gas suddenly comes out. Same thing happened at the lake. So this carbon dioxide flowed down the sides of the volcano, much like a liquid, into the nearby valley, pushed out all of the air with the oxygen in it, and killed more than 1,700 people and 3,000 head of cattle. It was a huge tragedy. So in an effort to keep this from happening again, scientists built a piping system to allow the carbon dioxide at the bottom of the lake to slowly vent as it's coming up. So this has been going on since 2001. It took them that long in this country to get that built and underway. So they were doing other things to try to keep the buildup from occurring again, but it took until 2001 to get this system underway, and it's been releasing the carbon dioxide so that this won't happen again. And they're slowly controlling the release of that carbon dioxide. But what this illustrates is that that mixture, that carbon dioxide and water mixture at the bottom of the lake, is a solution. A solution is a homogeneous mixture of two or more substances, and it doesn't have to be solid and liquid or liquid and liquid. There are all sorts of solutions. Most of the solutions that we are familiar with are liquids and gases, but you can have solutions of solids as well. If you're familiar with steel, alloys, any kind of an alloy, that's a solid solution. The ocean is a solution of salt and many other things dissolved in water. Blood plasma is a solution of several solids and ions, as well as different gases dissolved in a water base. A solution can be a gas and a liquid. It can be a liquid and another liquid, a solid and a gas, however you want to look at that. So table 13.1 in your book gives some common types of solutions. So gaseous solutions are gas and gas, and we're talking about here what we call solute phase and solvent phase, and we'll talk about what those mean in just a second. But an example of a gaseous solution that you're familiar with is the air that you breathe, mainly oxygen and nitrogen. There's some carbon dioxide in there, argon, there's all sorts of things in there. Liquid solutions, you can have a gas dissolved in a liquid dissolved in a liquid, a solid dissolved in a liquid. You can have solid dissolved in a solid. It goes on and on and on. Okay, the ones that we in particular will be focusing on are solids dissolved in liquids. That's a big one for us as chemists in the lab. And then gases dissolved in liquids. Those are going to be the ones we focus on. Although liquid solutions are also very important. They're important enough to have their own focus, and so those will be looked at later. So a solution has to have at least two components. Okay, you have to have the solvent, which is the component that is present in the greater amount, and a solute, which is the component present in a lesser amount. So again, it's not necessarily a liquid or whatnot. We're used to thinking of aqueous solutions where water is the solvent. It does not have to be that way. But in a solid liquid solution, generally the liquid is considered the solvent regardless of the relative proportions. So for example, if you've ever made candy, you know that you can dissolve a huge amount of sugar in water. So for example, if you're going to make there's a particular kind of frosting on cakes called fondant. To make fondant, you're going to start by dissolving 2 cups of sugar in 1 cup of water. And that's a little bit mind-blowing when you first think about it. In this case, the sugar is the one that seems to be in the greater amount, the water is in the lesser amount, but in that solution, you would still consider the water to be the solvent, the liquid. Okay, so solid liquid, you're going to go with the liquid as the solvent. And because water is our most abundant solvent, we use it commonly, that is a special class of solution known as aqueous solutions. And we've been talking about aqueous solutions with our net ionic equations and whatnot. This is where that's coming from. Okay. Other solvents are used all the time in the laboratory and industry, cleaning solutions in the home, especially if we want to form a solution with nonpolar solutes. So remember in chapter 10, we said that water is polar. So if we need to dissolve something that's nonpolar, water's not going to be the way to go. So we're going to look for a nonpolar solvent to dissolve that, such as grease or oil. So how do you know what solvent you're going to use? Well, there are some rules that you use for choosing a solvent, and one of them is that like dissolves like. Polar solvents dissolve polar solutes, nonpolar solvents dissolve nonpolar solutes. So there's a really kind of corny joke that goes around the chemistry circuits that you'll see right here. The polar bear has fallen in the water and he yells, "Help, I'm dissolving." Well, here comes the grizzly bear that says, "Well, bears are insoluble. That's easy for you to say, you're not polar." So a little bit of play on words there, really corny, but got to have a few of those. And if you look at table 13.2 in your book, it gives some examples of common solvents, both polar and nonpolar. So water is probably the biggest solvent that we have in the lab. It's polar solvent. We can use it all the time, but there are cases where water isn't going to work. You don't want water because of undesirable effects with something else. So a couple of others you could use are acetone or methyl alcohol. Okay, so these are all polar solvents. Over here are some common nonpolar solvents that you may see in the lab. Hexane, diethyl ether, toluene. Carbon tetrachloride used to be on that list, but it's been designated as a carcinogen. So it used to be used very commonly for dissolving grease and oil. It was used in automotive industry for dissolving grease off engine parts. So lots of different solvents that you can use. So when we say like dissolves like, polar and polar, nonpolar and nonpolar, what's going on with that? Well, the attractions between the solvent and the solute overcome the attractions that these solute particles or solvent particles already have to one another. So in this case, for example, here's the solvent, which is water. They're showing water molecules here. And there's an attraction to these water molecules, okay, shown by the dotted blue line. Same thing with this ionic compound, sodium chloride. There is a solute-solute attraction between the sodium ion and the chlorine ion. But when we mix the sodium chloride into water, suddenly there's this new attraction shown by the red dotted line that is stronger than the ones between these partial dipoles in the water or between even the ions in the sodium chloride. Now, to get a little bit better feel for that, to see that visually, we're going to look here. Hopefully there it goes, it'll pop up. Okay, so this is a visual. There's no sound with this, so I'm going to talk over the top of this, but it just shows how the positive ends of the water dipoles are attracted to the negatively charged ions in sodium chloride, the chlorine, the chloride ions, and then the negative ends of the water dipoles with the oxygen end of the water is attracted to the positively charged sodium cations. Now, if you look at figures 13.1 and 13.2 in your book on page 450, you will get a static image of that, but let's just look at the visual. So, okay, I'm going to mute that sound. There's some music with it, but there's no words or illustration with it. What they're trying to show here is how water is going to dissolve salt. So they show a water molecule with the two positively, the positive end with the hydrogen, the negative with the oxygen, a salt crystal. Yellow is sodium, purple is chlorine. Okay, now what they're doing here, they're using red to indicate the positive end, blue to indicate the negative end, the polar charge of the water molecule. Same thing within the sodium chloride. You have a red positively charged sodium ion, a blue negatively charged chloride ion. So notice here, when they're using this color designation, how it goes. Okay, the positive ends of the water are attracted to the negative end, and then the negative end of the water attracted to the positively charged ions. So they're like those little magnets coming together. Opposite charges. So when we say like dissolves like, it's because these are both charged, polar, but it's still that positive-negative interaction that's going on here. So the water molecules pull the sodium and chloride ions away from the crystal and out into the matrix of the water. So it's not really like they're flying in and grabbing one and pulling it out, but the water molecules are aligning themselves and surrounding, and they're working their way into the lattice and basically breaking it apart. So that gives you a visual of what's going on within that molecule. So when we look at a solution, there are some other terms that we look at. We talk about the solubility of a compound, which is defined as the amount of the compound, usually given in terms of mass in grams, that will dissolve in a certain amount, generally per either mass or volume of a liquid. Now, the solubility of sodium chloride, for example, at room temperature, because temperature affects the solubility, 25 degrees Celsius, is 36 grams of sodium chloride for every 100 grams of water. So if I were to measure out 36 grams of sodium chloride and pour it into 100 grams of water and mix that together, that would be known as a saturated sodium chloride solution. Okay, so definition number one here. A saturated solution is one that holds the maximum amount of solute under a particular set of solution conditions. So this means that if I were to take any more sodium chloride, I take another gram of sodium chloride and throw it in that solution and try to mix it in, it will not dissolve. It's just going to fall to the bottom of the container and sit there as a wet solid. An unsaturated solution is going to be one that holds less than the maximum amount of solute. And if additional solute is added to an unsaturated solution, it will continue to dissolve up until that maximum point. So if I only put in 30 grams of sodium chloride into 100 grams of water, I can add another 6 grams of sodium chloride. The 30 grams and 100 grams is unsaturated. And then there's a special case known as a supersaturated solution. And that is one that holds more than the amount of solute I would normally be able to put in. And that takes a special set of conditions. But what happens is it's temperature dependent. So generally, to make a supersaturated solution, what you're going to do is heat up a solvent, and then you're going to pour in the amount of solute that would dissolve at that higher temperature, which is higher. So let's say if I had 100 grams of boiling water, it would hold 50 grams of sodium chloride. So I get my water boiling, I pour in 50 grams of sodium chloride and get it dissolved, and then I turn off the heat and I just let it cool. And I don't bump it, I don't touch it, I don't let anything disturb it, I just let it cool down. Well, if nothing disturbs that system, it will cool back down to room temperature, but it will hold all of that solute still dissolved in solution until I tap it or disturb it somehow. And at that point, the solute will start to precipitate or become solid, come out of that supersaturated solution, and it will do it all at once, instantly. And there are some great visuals and examples of that. It's a hard situation to set up, so it's a little bit easier to see on a video than trying to do it yourself. But there are some great videos out there of that. And in the next slide, we have another little video it's a little bit on the corny side, but chemistry music video that just walks through the idea of solubility and saturation, and it will give you an idea of some of these things. And in particular, watch the video for the supersaturated solution that they show. See if you can catch that. Very corny, but it's a good way to get these ideas stuck in your head.
For those about to dissolve, we salute you!
Nice. Great, now we're gonna get sued by ACDC.
A salt dissolved in water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, the same throughout. Homogeneous, the same throughout. Solvents that are polar can dissolve solutes that are polar or ionic. That is really cute. Water and nonpolar solutes just won't mix, but a nonpolar solvent like benzene can fix. Like dissolves like polar and polar. Like dissolves like nonpolar and nonpolar. And all the solvent molecules used up and are stuck to the solute ions in your cup. Solution saturated, it is full for sure. Solubility's been reached for that temperature. Saturation on the line. Saturation on the line. If distill some water molecules unstuck, then more solute can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated, put more in. Unsaturated, put more in. If you put more solute in than can be dissolved, then a supersaturation situation's involved. The excess falls out as a precipitate, or the solution is unstable sodium acetate. Supersaturation, precipitate. Supersaturation, precipitate. A salt dissolved in water in a beaker today. The ions broke apart in the usual way. They made it harder for the water to boil and freeze, so the phase temperature changed a few degrees. Colligative properties depend on concentration. Colligative properties depend on concentration.
Electrolytes have a greater effect on the melting and boiling point of the solution than non-electrolytes.
More solute that's dissolved got more effect. Solution's boiling point increases direct. The freezing point decreases, which is really nice. In the winter, salt on roads can prevent the ice. Add a solute, boiling point goes up. Add a solute, freezing point goes down. That is wicked cool. Solutions rule.
Okay, so hopefully that wasn't too painful to watch. It was pretty short, just a little over 2 minutes, and it actually alluded to a couple of the properties we're going to be looking at in later sections of this chapter as well. But very nice overview of solutions, saturated, supersaturated, unsaturated. So hopefully you caught that supersaturated solution with the sodium acetate that was precipitating out of solution. Really, really interesting. All right, so a little bit more on supersaturated solutions. That's what happened at Lake Nyos. So it's a special circumstance. So when we carbonate soda, and put it in a soda can, we put it under pressure. So pressure and temperature are two things that can affect solubility of a solution. And when you open a soda can or a soda bottle, there's a sudden release of pressure, and it changes the solubility. So a can of soda is actually a supersaturated solution. It's actually holding more carbon dioxide gas than it would normally be able to because of the increased pressure. And as soon as that pressure drops, that's when the soda starts fizzing, because you've now changed its solubility. The gas is, quote, precipitating out of solution. Same thing that happened at Lake Nyos. It was supersaturated because the pressure dropped. So it was saturated when it was under pressure. As soon as the pressure dropped, it was supersaturated, and that excess gas had to come out of solution. It precipitated out, if you will, rose to the surface, and then got emitted into the surrounding air. Now, we've looked at solubility rules. What will be soluble in water? Solubility rules give us a qualitative description of the solubility of ionic solids. We do want to look at quantitative, but let's just look at the qualitative end first. So, for example, if we look at calcium carbonate, which is, if you remember from solubility rules, an insoluble compound, that means that the attraction between calcium 2+ cations and carbonate 2- anions is greater than those ions' attraction to the solvent, in this case water. So calcium carbonate doesn't dissolve in water. So the solubility of calcium carbonate is essentially 0 grams in 100 grams of water. There's a tiny, tiny little bit that'll dissolve, but not enough to be significant. Molecular solids can also be soluble in water, depending on whether or not the solid is polar. So, for example, we know table sugar dissolves in water, but it's not an ionic compound. So why does it dissolve in water if there isn't an ionic attraction? Well, that's because table sugar, even though it's not ionic, it is polar. It has a dipole. And so even though it's not a full charge, there's a partial charge there that can interact with water as a polar solvent. Now, we know that if we have nonpolar solids, things like vegetable oil, vegetable shortening, lard, and you drop those in water, they're not going to dissolve. They're insoluble. Nonpolar doesn't dissolve in the polar water. We want to also go back and touch on electrolyte solutions. And we've talked a little bit about electrolytes. So we know that an electrolyte is something that creates ions when it's dissolved in water. So an electrolyte solution, like Gatorade, contains dissolved ions or charged particles when in solution, and it will conduct electricity. Non-electrolyte solutions contain molecules that are neutral. So they're polar, but they're not ions. So sugar, even though it's polar and will dissolve in water, there isn't really an ionic charge on these individual molecules, and so they don't conduct electricity. They're non-electrolytes. Now, we said that there are different things that affect solubility, including temperature and pressure. So how do those affect it? And let's start with temperature. So in general rule of thumb, again, there's exceptions to every rule, but in general, if you have a solid dissolved in water, you're going to increase the amount of that solid you can dissolve in water if you increase the temperature. So iced tea, classic example. If you want to sweeten your tea, are you going to add the sugar while your tea is still warm after brewing, or are you going to add it once you've got it chilled and on ice? Well, it dissolves much better. The solubility of sugar in the warm tea solution is much higher than it is in the cold solution. So solubility of a solid increases with increasing temperature. And we'll look at gases, but it's kind of the opposite for gases. We'll get there. So we can look at temperature dependence of the solubility of a substance and use that to our advantage to help purify a compound. And this is a very common technique used in organic chemistry where a lot of compounds get synthesized. Drug synthesis and medicine synthesis relies a lot on recrystallization. So you may carry out a reaction that creates a compound that you want, but then there are also impurities in that compound. There are other molecules that may get made, or you may have parts of the reactants that, your excess reagent might still be in there, and you want to purify your solid. So you can use something known as recrystallization. That just means that you take the solid and you dissolve it in water or some other solvent at an elevated temperature, okay, to create a saturated solution at the elevated temperature, and then you let it cool. And as the solution cools, you have a supersaturated solution. It begins to precipitate out, okay, and as it precipitates, if it does so slowly being the key, the solid will form nice clean crystals as it comes out that tend to exclude the impurities. So the molecules of the thing you're crystallizing, just like the water and oil, they tend to want to cling together and not have other things trapped in their structure. So you end up with a much purer solid that way using recrystallization. You can also use this to your advantage to, again, work in the kitchen. So if you've ever made rock candy or seen rock candy, so these chunks of colored sugar on the end of a swizzle stick that you can stir into your coffee or tea or just eat that way. This is just the process of recrystallization. So what you do is you prepare a saturated table sugar solution at an elevated temperature. You take water, you put it on the stove, and then you stir in sugar until no more will dissolve in the hot water. You add food coloring to it at that point if you want, and then you pour it in a clean jar, and then you take a stick or a string and you suspend it in that solution, the hot solution, and you let it cool and stand for several days, and it recrystallizes. It cools very slowly, and the stick or the string that you put in there acts as what we call a nucleation point. It gives the crystal something to grow on. It gives it a base. And the sugar crystals will start to grow on the string or the stick that you put in there. As the solution becomes supersaturated, it cools, it evaporates, and there's more sugar in there than the solution can hold. It has to precipitate out. After several days, you'll get this cluster of these really pretty, sparkly rocks or crystals of sugar on your nucleation site, your string or your stick. And since it's table sugar with a little color in it, you can go ahead and eat that. Okay, that's all rock candy is. It's just recrystallized sugar. Now that's the case of solids dissolved in water. Let's look at what happens with gas in water. So let's look at our Lake Nyos, or let's look at our soda, our can of soda again. Okay, those were both examples of a solution of a gas dissolved in water, carbon dioxide in water. Now most liquids, when exposed to the air, do contain some dissolved gases. A lot of gases in the air will go ahead and dissolve into solution. So even your tap water that you have sitting out, it's exposed to air in a certain amount. There's going to be a certain amount of carbon dioxide that dissolves into water. If you were to take a sample of tap water and check the pH of it, if it had been sitting around for a while undisturbed, now when you run it and you run the faucet and you flush everything through, then it tends to drive out the dissolved gas. But if you've had a tank of water sitting somewhere for a while and you test the pH, you'll probably see that it's slightly on the acidic side because it's dissolving carbon dioxide and forming carbonic acid in solution. Now, lake water and seawater also contain dissolved gases. Dissolved oxygen, we know, that's how fish breathe. Okay, they don't breathe gaseous oxygen like we do. They get it from the dissolved oxygen in the water through their gills. Our blood, it's very important that our blood be able to dissolve gases such as nitrogen, oxygen, carbon dioxide. There's a lot of gas exchange going on in our blood. As I said, tap water, even your tap water will have some atmospheric gases dissolved in it. So gases dissolve into water fairly easily. The solubility of a gas in water is temperature dependent, but not in the same way as solids. It's the exact opposite. The solubility of a gas in water will decrease as you increase the temperature. If you take ordinary tap water and heat it up on the stove, you'll see those dissolved gases come out of there. before you reach the boiling point, you see a lot of small bubbles develop in the water. You get those tiny little bubbles that coat the bottom of the pan and the sides of the pan, and we think of those as the start of the boiling point. We think that, oh, it's starting to boil. It's really not the water boiling. What it is as we warm up the water, we're lowering its ability to keep those gases dissolved in the water, and they start to bubble out. So they're dissolved air. It's mostly nitrogen and oxygen just coming out of the solution. And then as the temperature of the water rises, the solubility continues to decrease. The gases come out of solution. We get those smaller bubbles. And then once we get the water boiling, the bubbling becomes much more vigorous. Okay, now in that case, the vigorous, the rolling boil that you get are water vapor. It's the water actually converting itself from liquid phase to gas phase. It's no longer the dissolved air. But the little bubbles you get to start with are actually just gases that were dissolved in the water coming out of solution. Soda pop, same thing. You can think of it that way. You know that if you have cold soda, it's going to remain carbonated much longer than a warm soda. So that's why once you've opened a soda, you store it in the refrigerator. You want to keep it cold because the solubility of the carbon dioxide is going to be higher. Okay, cold soda pop, they pour it, very little bubbling in there. Carbon dioxide still trapped in your soda. Warm one, you pour that, you get a lot of bubbling, a lot of fizzing. This soda is going to taste flat much more quickly because the carbon dioxide is coming out of the warm solution. So solid solubility in water increases with temperature, gas solubility decreases with temperature, increase of temperature. Okay, and this property of the gases is related to something called Henry's Law. And this ties in a little bit when we go back to pick up chapters 11 and 12. You'll see some more of this. But the idea behind Henry's Law is the pressure, the relationship of pressure to solubility. So the higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. So we know that for a can of soda, we put it under pressure in order to get that gas to dissolve. We want to pressurize it. We want to keep it cold. Lower temperature, higher pressure equals higher solubility for a gas. So our can of soda, we open it up. According to Henry's Law, we reduce the pressure. So that reduces the solubility of the carbon dioxide and it comes out of solution. All right, so I know that's a big chunk, but that is the first 4 sections of chapter 13. In the next part, we will look at some quantitative calculations that we can make for solutions, including mass percent and the idea of molarity. And I will let you know, molarity is a huge one in chemistry, and this is one you will be seeing from here on out. So make sure you really, really understand the idea of molarity.